In 2009, at the Hessentag Festival in Germany, engineers from the Hessen Energy Saving Initiative put a reconstructed Bronze Age wall to the test. The results were astonishing, revealing that this 3,400-year-old design met the building codes of 1995. What truly shocked them was the realization that between the Bronze Age and 1995, our insulation techniques had regressed significantly, becoming 4 to 6 times worse. It wasn't a matter of forgetting. We had actually moved backward. Imagine a medieval peasant in January 1320, facing temperatures of minus 40 degrees Fahrenheit without electricity or a heating system, yet remaining warm. Now, picture your modern home without power for 24 hours in such extreme cold, pipes freezing, walls cracking. What knowledge did these medieval peasants possess that we have since lost? Today, we'll explore 7 inventions that allowed peasants to survive winters that could prove fatal to us in mere days. Feel free to comment below with the coldest temperature you've ever experienced. Let's dive in. Invention number 1. The heat storage hypocaust, a heating system so efficient that modern technology still struggles to match its fundamental principle. You're likely familiar with Roman hypocausts, which provided underfloor heating in bathhouses through hot air circulating beneath raised floors. Impressive, yes, but with a critical flaw: the constant need for a fire. Wood had to be fed into the furnace continuously, or the heat would die along with the flames. Medieval monks in Northern Europe faced winters with temperatures commonly dropping to minus 20, minus 30, or even minus 40 degrees Fahrenheit. The Roman system was simply too inefficient, expensive, and labor-intensive. Around the 14th century, perhaps even earlier, medieval engineers achieved a breakthrough by adding thermal mass, massive granite boulders. Here's the complete system: a chamber dug beneath the floor, housing a barrel vault furnace constructed from stone or brick. Stacked atop this vault were granite stones, each 16 to 20 inches in diameter. These weren't just any rocks. Granite was specifically chosen for its unique thermal properties. The room above featured a perforated hot plate, essentially a floor with strategically placed holes that remained closed during the burning phase. The operation was ingeniously simple: light the fire once, allowing it to burn hot and fast for 2 to 4 hours. The flames and hot gases would heat the massive granite stones to temperatures exceeding 500 degrees Fahrenheit. The stones absorbed this thermal energy, storing it within their crystalline structure. Once the fire had burned out and the ashes were cleared, the smoke flue was closed to trap the heat, and the vents in the floor were opened. Physics then took over. Hot air rose from the superheated stone pile through the floor vents, warming the living space above. But this wasn't a fleeting burst of heat. The granite stones, now acting as a thermal battery, released heat slowly and steadily for 3, 4, 5 days, or even longer. A single firing could warm an entire living space for nearly a week. Consider the math. Burning a fire for 3 hours every 5 days averages out to roughly 36 minutes of active burning per day. Compare that to a modern furnace cycling on and off every hour, potentially running for 6 to 8 hours daily in the depths of winter. The medieval system required perhaps only 10% of the fuel consumption for comparable results. This system spread rapidly across Northern Europe. By the end of the 15th century, historians estimate that 800 to 1,000 heat storage hypocausts existed in the Baltic region alone. They appeared in monasteries, providing monks with reliable heat for copying manuscripts, in castles, ensuring the comfort of nobility, in town halls and guild halls, serving public functions, and even in the private homes of wealthy merchants. Remarkably, this was convective heating, not radiant. The Roman system heated floors, which then radiated warmth. The medieval system actively moved hot air through convection currents, a far more efficient method of heat distribution. Modern heating engineers didn't fully understand this technology until recent decades. Throughout the 1980s and into the 90s, standard histories claimed that Roman heating technology was mostly lost after the empire's collapse. They were unaware that medieval builders not only preserved the knowledge, but dramatically improved it. compared to your modern home, with its natural gas furnace or electric heat pump running constantly throughout winter, consuming natural gas or electricity nonstop and resulting in monthly heating bills in cold climates easily reaching $400, $500, or even $600. The medieval peasant with access to a heat storage hypocaust only needed to load firewood every 5 days. Even if the wood cost money, it was a tiny fraction of modern heating costs. If they gathered their own, it was free except for the labor involved. This represents a profound difference in technological philosophy. Modern systems prioritize convenience, instant heat at the flip of a switch. We've built infrastructure that requires constant energy input to maintain constant comfort. Medieval systems prioritized efficiency, work hard once, benefit for days, and use thermal mass intelligently, respecting the principle that captured heat should be stored, not continuously generated. Which approach makes more sense in a world facing energy constraints? Invention number 2. Lanolin-treated wool. Shifting from heating buildings to heating the body, medieval peasants possessed technology that baffles modern materials scientists. Fabric that becomes warmer when it gets wet. Sounds impossible, right? In 2015, a research team attempted to develop synthetic fabrics that could generate heat upon moisture exposure, but the project failed. The necessary chemical reactions were too complex and unstable for manufactured materials. Medieval peasants, however, accomplished this accidentally through sheep husbandry. The science is truly fascinating. Sheep produce lanolin, a waxy yellow substance secreted by sebaceous glands. Lanolin naturally coats wool fibers, serving multiple purposes, protecting the sheep's skin, regulating moisture, and providing water resistance. When a sheep is sheared, the raw fleece contains roughly 12 to 25% lanolin by weight. That greasy, almost sticky feeling of raw wool is pure lanolin. Modern textile manufacturing removes it entirely. We wash fleeces with industrial detergents and hot water in a process called scouring.
Why?
Because consumers want wool that looks clean, feels soft against the skin, and doesn't smell like sheep. So, we strip away the lanolin completely, often selling it separately to cosmetics companies for use in lotions and creams. Medieval peasants couldn't afford such waste. More importantly, they discovered through generations of experience that lanolin-rich wool had properties bordering on miraculous for cold weather survival. 3 key properties made it revolutionary. First, natural water resistance. Lanolin creates a waxy barrier that repels liquid water. When rain hits properly treated wool clothing, water forms beads on the surface and rolls off rather than soaking in. While not completely waterproof like modern Gore-Tex, it's water-resistant enough to allow working outdoors in light rain or snow for hours without becoming dangerously wet. For medieval peasants who spent entire days outside tending livestock, harvesting crops, or performing manual labor, this was critical for survival. Second, moisture absorption without saturation. This might seem paradoxical given the first property, but the wool fiber structure explains it. Wool can absorb up to 30% of its own weight in moisture vapor before feeling wet to the touch. The fiber structure has scales that channel water preferentially toward the garment's hem. This means moisture collects at the bottom edge, where it can drip away, while the upper portions of the garment closest to your core body remain relatively dry. You could sweat heavily inside wool clothing or have snow melting against it, and the garment would still maintain its insulation properties. Third, and this is where it becomes almost magical, wet wool generates heat, not perceptually, not metaphorically, but actually measurably, chemically generates thermal energy. Here's the mechanism. The outer surface of the wool fiber, called the epicuticle, has microscopic pores. When environmental humidity is high, these pores actively draw in moisture vapor from the surrounding air. Water molecules enter the fiber core through these pores. Inside the fiber, water molecules encounter the complex protein structure of keratin, the primary component of wool. A chemical reaction occurs. The hydrogen bonds in H2O molecules break apart. These broken hydrogen bonds then form new chemical bonds with the amino acid chains in the wool protein. This bond formation is an exothermic reaction, meaning it releases energy in the form of heat. Modern laboratory tests confirm this. When wool absorbs significant moisture, temperatures in the fabric can increase by several degrees. It's not a huge amount, but in survival situations, every degree matters. When you're already on the edge of hypothermia, a few degrees of additional warmth can be literally life-saving. Compare this to cotton, humanity's other major natural fiber. When cotton gets wet, it conducts heat away from your body 150 times faster than when dry. Wet cotton clothing accelerates hypothermia. This is why experienced outdoors people have a saying, "Cotton kills." Synthetic fabrics, for the most part, lose their insulating air-trapping capacity completely when saturated. Polyester fleece, when soaked, provides almost zero warmth. Nylon does the same. But medieval wool continued functioning, actually improving performance in wet conditions. Medieval peasants built their entire cold-weather survival strategy around wool. They understood layering long before modern outdoor education programs taught it. The innermost layer was a linen shirt or chemise against the skin, which wickeded moisture away from the skin surface through capillary action. Next came a wool tunic or coat, followed by another wool tunic, and then a thick wool cloak. The total thickness could easily be 4 to 6 inches of layered wool. For the legs, they wore wool hosen, basically fitted leggings. In extreme cold, they would layer 2 or even 3 pairs of hosen together. Wool hats covered the ears and neck, and wool mittens, often with separate outer mittens, provided double protection. Every garment was wool. And it worked. Medieval chronicles and records describe people working outdoors through brutal winters, with temperatures well below freezing, without the frostbite injuries or hypothermia deaths that we would expect. They understood intuitively what modern science has since confirmed. Wool is the king of cold-weather survival fabrics. The modern outdoor industry is slowly, reluctantly rediscovering this ancient wisdom. Merino wool base layers now command premium prices, $50 to $100 for a single shirt. Wool socks, wool mid-layers, and wool outer garments are all marketed as high-tech solutions. As for the lanolin, most manufacturers still remove it, though a few specialty companies now advertise raw wool or lanolin-rich products at 3 to 4 times the cost of regular wool. Medieval peasants had this superior technology as their default everyday clothing, what we now sell as premium outdoor gear. They considered it a basic necessity. Invention number 3. Wattle and daub double wall construction. The same 2009 German reconstruction that opened this video revealed something that should humble every modern builder: the Bronze Age wall's thermal performance, boasting a U factor between 0.5 and 1.0 West per square meter Kelvin. For context, that matches German heat protection regulations from 1995. This design was 3,400 years old. The testing engineer published findings with a remarkable statement: "We should very humbly acknowledge that comparable high insulation values were not reached again until the heat protection regulation of 1995. In the thousands of years in between, the insulation grew 4 to 6 times worse with timber-framed houses, 3 times worse with solid brick walls." Translation: for over 3 millennia, human civilization regressed in thermal building performance. We didn't maintain standards, we got dramatically worse. The superior technology that we forgot and then relearned: double-walled wattle and daub construction. Let's understand what this means. Basic wattle and daub is simple in concept. Create a woven lattice of thin, flexible wooden branches called wattle. Think of basket weaving applied to walls. Then, cover this lattice with daub, a mixture of wet soil, clay, animal dung, and straw or other fibrous material. The daub dries hard, creating a solid, if somewhat irregular, wall surface. That's the simple version used in many cultures. One wattle layer with daub applied to both sides. It provides decent weather protection and moderate insulation, but nothing exceptional thermally. The advanced version, developed in the Bronze Age and maintained through medieval times, used 2 parallel wattle layers with a critical insulating cavity between them. The construction process worked like this. First, build your primary wattle panel with vertical staves driven into the ground or secured to the building frame. Horizontal-wise, typically willow branches, are then woven between the staves, creating a flexible but stable lattice. Apply daub to the exterior face, building up layers until you have a weather-resistant surface perhaps 1 to 2 inches thick. Now for the crucial step. Instead of daubing the interior face immediately, construct a second wattle panel parallel to the first, leaving a gap of 4 to 8 inches, depending on climate severity. Northern climates used wider gaps. Fill this cavity with dried grass, not loose grass, but densely packed. This is critical, as the grass needed to be tightly packed to prevent air circulation while maintaining its structure. Proper grass packing created millions of tiny air pockets, each too small for convective air currents. Air, when still, is one of nature's best insulators. Its thermal conductivity is extremely low. The challenge is keeping air immobile. If air can circulate, convection rapidly transfers heat. The grass matrix solved this beautifully, with each blade of grass dividing the cavity into microscopic still air chambers. It was perfect insulation using the most abundant material imaginable. After packing the grass cavity, apply daub to the interior wattle, completing your wall sandwich. Exterior daub, wattle, grass cavity, wattle, interior daub. The sophistication here is remarkable. Both daub layers provided thermal mass, absorbing heat during the day and releasing it slowly at night. The grass cavity provided the actual insulation barrier, preventing heat transfer. And because all materials were naturally porous and breathable, moisture could gradually migrate through the wall without accumulating, preventing rot and mold. Wall thickness varied by climate. Moderate regions like southern England might use 4-inch cavities, while harsher northern areas like Scandinavia or northern Germany use 6 to 8 inches or more. Some archaeological finds suggest cavities as wide as 12 inches in the coldest regions. The materials were locally sourced and essentially free. Willow or hazel branches for wattle grew abundantly near streams and wetlands. Grass covered every field. Clay came from the ground beneath your feet. Straw was harvest waste and animal dung was, well, animal waste. Zero material cost. It was labor-intensive, yes. Building a complete wattle and daub house required community effort, but the materials were free. Compare this to modern insulation technology. Fiberglass bats manufactured in factories from melted glass fibers, foam board insulation made from petroleum-derived polymers, or spray foam requiring specialized equipment and chemical expertise. All these products require industrial manufacturing, chemical processing, energy-intensive production, and, of course, money, lots of money. A modern home's insulation package can easily cost $10 to $20,000. Medieval peasants built comparable or superior thermal performance from materials they gathered themselves. But here's the tragic irony. Despite having this proven technology for millennia, we abandoned it.
Why?
Partly because we could. Industrial materials seemed more modern and advanced. We built thinner walls because we could engineer buildings differently. We prioritized construction speed and cost over thermal performance, assuming that technological progress meant abandoning old methods. Only in 1995, after decades of energy crises, after computer modeling, and after modern building science matured, did we finally achieve thermal standards that Bronze Age builders had mastered with grass and mud. Medieval peasants, maintaining this tradition, understood something we're only now relearning. The simplest solution using the most basic materials is often the most sophisticated when properly understood. Invention number 4. Peat and turf burning. Hypocausts needed fuel. In medieval Northern Europe, wood was scarce. Forests were cleared for farmland, and the remaining timber was too valuable to burn. So, medieval peasants burned the earth itself. Peat. Peat is partially decayed plant matter from wetlands, forming over thousands of years. It's dense and spongy, somewhere between plants and coal, with an energy density of 15 to 17 megajoules per kilogram, nearly identical to dried wood. It offered 3 key advantages. First, abundance. Vast peatlands covered northern Europe, Ireland, Scotland, the Netherlands, Germany, Scandinavia, and England. Second, continuous formation. Peatlands produced 1 millimeter yearly, making medieval extraction sustainable. Third, energy independence. Consider the 17th century Netherlands as an example. They consumed 25 million gigajoules of peat annually, with a population of 1.5 million, which equals 16.75 gigajoules per capita yearly. Today's global average is 76.6 gigajoules per capita. The Dutch used 1/4 of modern consumption. Critically, peat handled their heating needs, so imported wood went to construction and shipbuilding, generating higher economic returns. This helped the Netherlands become a maritime power. The process involved cutting peat blocks in the spring and summer and stacking them to dry for weeks or months. Raw peat is 95% water. Dried peat burns slowly and steadily, making it ideal for heat storage hypocaustes, requiring only one load every few days. Its calorific value is 9,200 to 9,800 BTUs per pound when dry. With lower sulfur content than coal, it produced cleaner smoke for home heating. Today, we've abandoned peat for fossil fuels, losing local energy security. Medieval peasants walked to the bog and cut free fuel. There were no supply chains, no imports, no infrastructure dependence. Your modern home is completely dependent on power grids, gas pipelines, and oil deliveries. Any disruption means immediate trouble. The medieval system was resilient, decentralized, and sustainable. Invention number 5. Root cellars. Warmth is half of survival. Food is the other half. In winter, nothing grows. Everything freezes. The modern solution is refrigeration, running 24/7 on electricity. The medieval solution? The earth itself, root cellars. They operated on 3 principles. First, temperature. The earth below the frost line maintains 32 to 40 degrees Fahrenheit year-round, just above freezing, perfect for storage. The frost line depth varies by climate, with northern regions typically seeing 4 to 6 feet. Medieval cellars went 6 to 8 feet deep, lined with stone for stability and thermal mass. Second, humidity. Vegetables need 85 to 95% relative humidity to prevent drying. Earth naturally provides this. Soil moisture and stone walls wick moisture, creating high humidity without mold. Third, ventilation. 2 openings create natural convection. Cold air sinks through one, while warm, stale air rises and exits through the other. This prevents ethylene gas buildup, which accelerates spoilage. Sophisticated designs use double-door airlocks, requiring you to enter the first door, close it, and then open the second, preventing warm air disruption. The results? Carrots, turnips, beets, and parsnips last 6 to 8 months. Potatoes last 6 to 8 months. Cabbage lasts 3 to 4 months. Winter squash and pumpkins last 6 to 8 months. Some cellars even allowed for continued growth, with transplants of leeks or celery into the cellar's soil floor in the autumn, staying alive and providing fresh greens all winter. Compared to modern storage, a refrigerator consumes electricity constantly. A power outage for one day can cause everything to spoil. A root cellar requires 0 energy, no moving parts, no electronics, and no infrastructure dependence. Medieval peasants built these into hillsides or under homes with trapdoors. Communities sometimes shared cellars. There was 0 energy input, just checking stored food and removing any spoilage. Medieval survival depended on this knowledge. Invention number 6. Log cabin design. The building itself. How do you construct shelter that keeps heat in using only local materials? Medieval Northern Europeans developed the notched corner log cabin, built upon key principles. Massive wood walls were constructed with logs 8 to 12 inches in diameter or thicker, providing enormous thermal mass. The walls absorb heat during the day, releasing it slowly at night, minimizing temperature fluctuations. Notched corners were used without nails or pegs, instead utilizing interlocking cuts that fit precisely. As the logs dried and settled, they compressed tighter. Wood expands and contracts with temperature, seating tighter into the notches over time. The result was no gaps, no air leaks, and an almost perfectly sealed structure. Modern homes often use dimensional lumber, drywall, and thin walls with lots of seams, leading to air infiltration and constant cold drafts everywhere. Medieval log cabins, once chinked with moss or clay, were remarkably airtight, with minimal openings, small windows, and thick doors. Every opening is a thermal liability. Heavy thatch roofs, 2 feet thick, provided excellent insulation, or sod roofs were used, with birch bark waterproofing plus soil and grass, adding massive thermal mass. One central hearth burning steadily was enough. Modern stick-built homes need constant heating operation, while log cabins required only periodic fuel addition. Which design survives a power grid failure during a polar vortex? Invention number 7. Medieval chimneys and stone stoves. Finally, the hearth itself, the fire making everything possible. Early medieval homes used central fire pits, with smoke drifting up through roof gaps. This was inefficient and dangerous. Smoke inhalation was a health problem, and heat escaped with the smoke. By the later medieval period, 2 innovations emerged, the chimney and the masonry stove. The chimney directed smoke up and out through a dedicated flue, eliminating interior smoke and, more importantly, controlling airflow. Medieval chimneys used large stone or brick hoods, funneling smoke from open hearths. The hood created a chamber above the fire, allowing heat to radiate outward before the smoke escaped. The hood acted as a heat exchanger, spreading heat through the masonry and radiating warmth for hours instead of rushing straight out. Benches, or sleeping platforms, were built adjacent to the chimney mass, as the stone stayed warm long after the fire died. The real breakthrough was masonry stoves, Kachelofen in German and Pechka in Russian, developed in the 14th and 15th centuries. Building on medieval principles, these weren't open hearths, but rather a chamber with a small door for fuel. The fire burned hot inside, heating a massive stone, brick, or ceramic tile structure. Internal channels forced smoke and hot gases through a long, winding path before exiting. As the gases traveled through the channels, they transferred heat to the masonry. By the time the smoke exited, it was relatively cool. Almost all the heat was extracted and stored in the stone. The result? You could build a hot fire for 2 to 3 hours, then close the damper, and the masonry mass would radiate warmth for 24 hours or more, requiring only one firing daily. Compared to an open fireplace, where most of the heat goes up the chimney, or a modern furnace, which cycles constantly and burns fuel continuously, medieval engineers understood thermal mass. Stone and ceramic store enormous heat. They designed systems that captured and held fire heat for hours. We generate heat on demand, blowing hot air around, but don't store it efficiently. The medieval hearth was a sophisticated heat capture, storage, and distribution system built from stone, requiring no electricity, no complex controls, just knowledge, skill, and respect for keeping heat instead of wasting it. 7 technologies, 7 ways medieval peasants survived -40 degrees Fahrenheit weather. Heat storage hypocaust provided 5 days of warmth from one fire. Lanolin wool generated heat when wet. Wattle and daub matched 1995 insulation standards. Peat burning ensured local energy independence. Root cellars offered 8-month storage with 0 electricity. Log cabins provided thermal mass and perfect sealing. And masonry hearths captured and held every degree of heat. These weren't primitive technologies. They were sophisticated applications of physics, material science, and engineering, demonstrating a deep understanding of thermal dynamics, moisture management, and resource efficiency. Modern technology has given us conveniences, but we've lost resilience. Medieval systems didn't depend on supply chains, power grids, or fossil fuels. They relied on local materials, passive physics, and renewable resources. They worked for centuries, and many buildings are still standing and functional today. How many modern homes will survive 500 years? How many will keep you alive if the power fails for one winter week? The lesson isn't about abandoning modern technology. It's about remembering principles we may desperately need again. Climate change is making weather more extreme, infrastructure is aging, and energy systems are straining. The stability we take for granted may not last. Maybe we should remember what worked, what kept people alive thousands of years before electricity, what worked in -40 winters with local materials, human knowledge, and clever design. The medieval peasant had independence, resilience, and the knowledge that survival didn't depend on uncontrollable systems. Which technology surprised you most? Which should modern society rediscover? Drop a comment below. If you enjoyed this video, hit like and subscribe for more practical wisdom from the past. Sometimes old ways weren't primitive. They were perfected. Thanks for watching.